Now let's look at some applications of total internal reflection. Of course, the most prominent application that you all probably know is guiding light in fibers. So all our telecommunication is basically based on these fiber optics where they use infrared light that is guided by fibers. How do they work? Well, they have a core, like you see here, and what is called a cladding and a coating. The coating is protecting the fibers from being damaged. The cladding is a different material that has a lower refractive index than the core material. So this way we get a little bit of a difference in refractive index between core and cladding, coming from the dense medium towards the optically thinner medium. And now we have total internal reflection. Of course, not at such a high angle typically as it is shown here, but typically at a relatively low angle, and then we can guide the light, and the quality of the material nowadays is so great that you can basically guide it for many kilometers without a loss in light intensity, and you get millions of reflection and not lose the energy. So inside that fiber it looks like this. Essentially you're going this way and this way and this way, and you continue like this. So if you go to the wave optical model, you will have to refine this a little bit, and there's different types of fiber depending on the size of this core material. If it is small enough, it is just big enough to guide one, what is called mode of the light. So an electric field distribution that just has sort of one maximum and goes down again, and that stays like this, and then it basically alters this idea a little bit. You would then say you have everywhere these reflections all the time, right? So now we are going to continue with a number of experiments in a row. So we will have a curved glass rod to show you what is called frustrated internal reflection. If we embed the glass rod in some medium, we will not be able to have internal reflection anymore because the refractive index difference is gone. We have a model of imaging fibers, so many fibers to transmit not only information in a single fiber, but a whole image simultaneously, as for example used in some endoscopes. We have what is called the reading stone, which is a particular gypsum material that is cut perpendicular so that it has something very similar to this imaging fiber model, but occurring in nature. We have an image conducting endoscope as it is used in medical imaging.